Now let's move on to the step 5, which is focused on identification of optimal solution. Okay. In this step, what we do is we combine the information from both the plots of the constraint functions and also the plot of contour plots of the objective function. So what we have from the previous plot, that we had this 4 constraint which was plotted here, and this was essentially the constraint function graph that we got after plotting all the inequality constraint. So that was one step. And then in the next step, we essentially plotted contours of the objective function. You can see these are the different contours that we have plotted, and this is essentially objective function contour plot and contour graph. So this is something that we have constructed previously. Now, when we go into identification of the optimal solution, what we do is we superimpose both of this graph together on top of each other and see how they look like. Okay, so the next step will be essentially superimposition of these two graphs together. So once we superimpose that, you will essentially get this resultant graph where you have the graph previously with respect to the constraint functions and also the hash line which are representing the objective function there. Now, as I mentioned, right, if you move in this direction, probably you are decreasing the objective function values. So the objective function values, the fx1, x2, right, was minus 50 here. But if I move in this direction and if I draw another line parallel to this line, right, this is for that line, maybe the objective function value will be minus 55. So it's decreasing. And if we keep on in this direction, the objective function value is going to be decreasing, or the ISO value of the ISO contour value of the objective function is going to be decreasing. Whereas if you're going in this direction, the objective function values are going to be increasing. When I say increasing, it will become from minus 50 to minus 40, minus 30, 0, and they will become 5 and 10. So which is increasing in this sense, right? So we know that if you move in this direction, then we are going to be basically moving in the direction where the objective function values are decreasing. So that is an approach we will take, and what we'll do is we know that the boundary which is defined by these 4 points which are there. Now let's mark those 4 points. Right. So this point, let's mark this point by A. This red point, which is intersection of G1 and G2. This point by B. Okay. This point by C. Okay. And this point by D. Okay. So A, B, C, D is the region that defines feasible solution. Okay. And remember, in the first class when we talked about solving optimization problem, first thing that we need to do is we need to make sure that whatever solution that we arrive at, that respects all the constraints that we have, and that is what is meant by feasibility. So if I pick any point inside this ABCD region, this point is going to be feasible. Whereas if I pick some point here, this is essentially going to be an infeasible solution, an infeasible point. So I cannot take this as a solution because this is going to violate the constraints that we have set for the problem. Whereas if I choose this problem or choose this point is essentially a feasible point, and it will satisfy all the 4 constraints that we have for our problem. But this point might not be the optimal point, and in fact I can see that the region that defines A, B, C, D, there are infinitely many points that are lying in this region, right? And so we have infinitely many solutions in this region. Okay. So the question is, which point do I pick out of this infinitely many feasible region, that is in infinitely many feasible points that lie in the region ABCD but is also optimal? Okay. Now remember, what is optimality? One way to think about optimality is it is the feasible solution point, or it is a point which is feasible but at the same time it has the least function values among all the points that are feasible. So what we need to do is, we know that this point or the whole thing is going to lie here, but we can use this contour plot guide to find feasible points that are going to be having minimal value. So one of the ways to do this is, okay, if I take this contour, and we know that we are moving parallel to this contour right here, right? So this is going to be a line, essentially a hashed line, which is going to have smaller value of objective function than what minus 50 is. Okay, so if I keep moving down here and keep moving parallel to this line, I keep moving in this direction, I will come and I will intersect at this point A, and that is the point, or that is the line that will basically give me feasible, that will lie in the feasible region, and that will have the lowest value. So you can see I have drawn one of the counter plots which is given by this counter plot that is passing through A, and that is parallel to the one which is minus 50, but this is where I will have the minimum value of the objective function, and at the same time, since this lies on the boundary of the region ABCD, it is going to be feasible. If I move beyond this and if I have a line parallel here, obviously this line is going to have a lower objective function value, but this line is not going to be lying in the feasible region because it's going to violate the constraints that we have, right? So even though this one has a lower objective function value, this is in the infeasible region, and that is not going to be the solution of the problem. And so I can approach this problem and start moving, and as I move from here, as soon as I touch the feasibility region, and this is the line that will be feasible, simultaneously feasible, and at the same time it will have the lowest function value possible for this. So from this we can see that either I can approach this problem from this region or approach this problem from here, this region, where I'm going from feasibility to infeasible region, or if we becoming infeasible to feasible region, and I can see that the point A, or the line, parallel line, the contour line that passed through A, is essentially going to be the line that defines, or that essentially identifies what is going to be the feasible point, and at the same time the point that has the least objective function. So from this approach we can identify that at this point, right, this red point, the point A, is the point which is feasible and at the same time has the lowest possible objective function value among all the points that lies in the region A, B, C, D. And this is how we can locate the optima in this overall problem that we have. Okay, so that is an approach that we will use to find the optimal location or optimal solution of this overall problem. Okay. So what we are doing, again, we will move away and we will find this A, and A is going to be essentially the point that will have the smallest objective function value. And then what we'll do is we will find out the coordinate of A. So we know that this point is going to be the one which is going to be the, so what is the coordinate and how I can find the coordinates? I project this on x-axis and then I project this on x2 axis, and from there I note down what is the projection of this point on x1 axis and what is the projection of this point on x2 axis, and it will come out to be 4, 4 and 12. Okay, and that coordinate, or the point of this A, which 4, 12, is essentially corresponding to x1 star or x2 star values that we were looking. Remember that previously we used an optimization approach or an analytical optimization approach to find x1 star values and x2 star values, but this is how you can use a graphical approach and find. So essentially x1 star will be equal to 4 and x2 star is going to be equal to 12, and that will give me essentially the optimal solution to this overall problem. Okay, and this is how we find out, or identify the optimal location of the optimal solution point using a graphical approach. Okay, so we read the coordinates which leads to x1 and x2, and then once we know what is the location of x1 star, x2 star, I can substitute that, and I can also find out what is the lowest value of the objective function that we can get while being feasible, while being respecting all the fold constraint, and that will come out to be minus 88. So at x1, x2, this will be minus 88. Or another way to say that is this contour that you see, right, this contour that is passing through this one, this contour value will be minus 88. And as you go beyond minus 88, your solution will become infeasible. Okay, so this is how we can essentially identify the location of the optimal point in an optimization problem using a graphical approach.